general relativity, step by step. I've been making heavy weather of the fact that if you've got a scalar phi defined at this point A and at this point B, and you try and figure out what this guy is, phi dash, is that a phi or psi? That's a phi, I think. Anyway, it doesn't matter whether you climb the hill that way or that way, you get to the same answer. That's great, and that's a sort of useful, kind of interesting thing to want to know. The ultimate view of it, the ultimate explanation is that the curl of any gradient is equal to 0 identically. Okay, so what I want to do now is to talk about, instead of taking a quantity phi from place to place, there's A along some path to B, I want to transport a vector. So here it is. I want to transport this vector here. So I'm sort of walking along this path here, pointing in a particular direction. And I want that vector to be constant. So how do I do that? Well, first of all, we'll go back to black. What I really want is to quantify the path. So the coordinates xi are in fact functions of some scalar lambda, and that lambda there is the path variable. So as lambda here, you might say lambda equals 0, and at this point here lambda equals 1. So it's just an index for how far along the path you are. Index for distance along the path. Actually, distance is a poor word, because I could have my path here, and I could have lambda equals 0 there, and at this point I could have lambda equals 1, but that point there might be lambda equals 0.5. So I might have it very stretched. In terms of lambda, you might be moving really quickly, and then very slowly there. And we'll see lots of applications of this in a little while. So I say distance along the path. It's really, distance is a poor word. Progress along the path. And what we want is that d by d lambda of, let's say, v equals 0. We want this to be the case. Well, that's great. So how do we do that? Well, what I'm going to do is I'm going to specify that v for my vector equals actually a function of lambda, because it's how far along this path we've gone here. And so I'm going to write it in component form as v alpha, let's say, of lambda. But then this vector here is composed into components. Been doing a bit of Fourier analysis. E alpha also of lambda. Because in a general curvilinear coordinate system, all your vectors, all your basis vectors are changing. So let's have a look at this, and we've got dv by d lambda is now equal to what? Well, it's dv alpha by d lambda e alpha plus v alpha times di by di lambda of e alpha. So we've got two components here. We've got the vector itself changing, or we've got the components of the vector changing. This is the comps, the components changing, of v changing. As it happens, in this kind of example that I drew up here, they're all the same, but it doesn't matter. And then we've got this component here, which is the basis vectors changing. Okay, so I'm going to need to do some tensor juggling to sort all this out. So what does that equal? Well, it's dv alpha by d lambda e alpha, summed over alpha, of course. Just pick up again how powerful that summation convention is. Plus v alpha. Now what I need to do is to replace this. D by d lambda has to go to dxi by di lambda di by di xi. I'm going to use that transformation, summed over I, of course. Actually, I'm using Greek letters here, so I better use Greek letters here. di x, no, I've got an alpha already, beta by di lambda, di e alpha by di lambda. Oh, not by di lambda. I've got a lambda there. That's going to be x beta. Right. Equals what? Let's start fooling around with this. dv alpha by d lambda e alpha plus v alpha di x beta by di lambda times this thing here. See if I can get this right. That is going to be a Christoffel symbol contracted on the top thing. We've got a gamma left over, a gamma left over. We've got an alpha and a beta. The beta sum there. Now, of course, what I want to do is to factorize it. So we've got this thing and this thing here, and I want to make them both alphas. Actually, I'll make them both gammas. It might be easier. dv gamma by d lambda e gamma. You see, nothing's changed. All I've changed is this umbral index here. We're summing over a different thing, and I've just called it a different index, that's all. And now I can leave this guy here because I want to factorize. Gamma, alpha, beta, basis vector, gamma. Equals E gamma. Now I'm going to factorize it, and we've got no, that's a straight D, plus V alpha, di x beta by di lambda, Christoffel symbol alpha, no, it's a gamma because it's contracted on that thing there, alpha beta. What was this thing? This thing was, sorry, a little glitch there. What this thing was dv by d lambda. So that's dv by d lambda equals this thing here. So what we say is, we call this thing here, call this capital dv, what letter am I using? Call it an alpha by di lambda, and that thing is equal to di v gamma by di lambda plus v alpha di x beta by di lambda times the Christoffel symbol. And we want this to be equal to 0. Want this to be equal to 0. Want this to be equal to 0. So what have we got? We've got the vector itself changing as we go along. It's not the vector itself, it's the components of the vector. These are the components of the vector changing. Plus a term that accounts for the fact that the coordinate bases themselves are changing. It's a little bit cheeky, this. I mean, I've made a slight lacuna here because we've got our little path here, and of course things are moving along there. But in order to evaluate these guys here, we need to make sure that the vector is nice and smooth in the vicinity of that path, and that's effectively what I've assumed. It's a little bit non-rigorous, but we'll leave it there. Okay, I'm going to stop there. That is called. I'm not going to stop there at all. I'm going to just define this as this is the intrinsic derivative of V alpha along the path xi equals xi of lambda, given by this differential here. Intrinsic derivative. Sometimes it's called the absolute derivative. And frankly, have I got this right? Yes, sometimes, yeah, you see lots of different, I'll put a capital D there. Some people have different notations. Sometimes I've seen dv alpha by little gamma there, little lambda. I've seen all sorts of peculiar notations. It's all a bit confusing. The intrinsic derivative or the absolute derivative, which is this thing here, which accounts for the fact that the coordinate bases are changing. And you account for that fact by putting the Christoffel symbols in here. Brilliant. I'm going to stop there. Stop.